This is our video for Unit 8, Day 6. What we're looking at today is infinite geometric series. So yesterday we looked at introduction to a geometric sequence, what that means, what the pattern looks like, and also how to find the sum of the first n terms of a geometric sequence. Today we're going to look at infinite geometric series. What happens when we add these terms up infinitely? So a geometric series has this form. So it's the same as for our geometric sequence. We have our first term a1, we have our common ratio r, and we multiply by another power of r every time to get our next term. The difference here is that it doesn't stop at n. So it keeps going infinitely, or another way of saying that is n goes to infinity. So we're going to look at today is, even though we're adding infinitely many terms here, sometimes this will have a finite sum. So there are special cases where we can add up infinitely many numbers that will add up to a finite sum. And that's what we're going to look at today. And to point out, we've been using these terms in our last two videos. I want to go through the difference real quick between a sequence and a series. So what the difference is, when we refer to a sequence, we're referring to just the terms themselves in the sequence. Refer to a series, we're referring to the sum of the terms. So we're talking about adding up infinitely many terms in a sequence, and seeing whether or not they will come to a finite sum, or the series will come to a finite sum. We have to see whether or not the series converges or diverges, whether um, it comes together and has a finite sum, or if it just keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. So we'll go through definition for what convergence means. A series converges if the sums of the sequence of the first n terms are going to approach a constant as n goes to infinity. So if we look at the sums of the first n terms and we let n go to infinity, if those sums are approaching a constant, then we say the series converges. So this is what converges means. So it means a series basically approaches a point as n goes to infinity. So what we really mean by this is we make in the number of terms we're adding up bigger and bigger, but the sums will approach the same number. And our notation we have for the sums, Sn, these are going to approach the same number. So first, you might not understand is how can we add up infinitely many numbers, but it comes to a finite number. It doesn't get any bigger, doesn't get any smaller. Um, so how is this possible? And that's what we're going to go through on the next slide. A test to see how this is possible. So what we're looking at here is called the ratio test. And what we look at is the ratio of the next term to the previous term throughout the entire series to see if the terms are getting smaller or if they're getting larger. So what we look at is this ratio of an plus 1 over an. And the absolute value of that as n gets larger goes to infinity. So what are these terms doing as we go further and further out, as we get larger and larger term numbers? So there's three cases. If this ratio is less than 1, so it's a proper fraction, then we say the series converges. If that ratio is greater than 1, means the terms are getting larger as we get more and more terms, then the series diverges. And the third case is if that ratio equals 1. In that case, it could do either. We need to use another test. So the reason this is called the ratio test, because what we're looking at is the ratio of the next term to the previous term as n goes to infinity. So as we get larger and larger, further and further along through our sequence. So we're going to do a couple examples of using the ratio test to see if a sequence will converge or diverge. So first one, 3, 9, 27, 81. So we'll know if this is convergent or divergent. So you can see each time that we're multiplying by 3, so that makes this a geometric sequence with common ratio 3 and first term 3. So we want to look at the ratio as n goes to infinity of the next term to the previous term. What that means in the case of this geometric sequence, we're looking at a1r to the n over a1r to the n minus 1. Right, so putting in the numbers we have, that means we're looking at 3 times 3 to the n, 3 times 3 to the n minus 1. Right, so our 3's right here will cancel out. Our 3n minus 1 will cancel out n minus 1 powers and leave 1 power of 3 left over. So our ratio of the next term to the previous term is 3. And since 3 is greater than 1, the series diverges. So another example, if we had the series or sequence 1, 1/2, 1/4, 1/8, 1/16. It's also a geometric sequence. This one has a common ratio of 1/2, and our first term is 1. So again, it's going to still have this same form. We're just going to have to put in our new numbers that apply to this problem. So the first term is 1 times 1/2 to the n over 1 times 1/2 to the n minus 1. And again, we see the same kind of cancellation. 1 and 1 cancel out. 1/2 to the n minus 1 cancels out and leaves just 1 power of n, or of 1/2 left on top. So we just have 1/2, and since 1/2 is less than 1, our series converges. So this test is actually really easy to use with the geometric series, because for geometric series, we already know the ratio of the next term to the previous term because it has a common ratio. So if we know it's a geometric series, all we need to look at is what that common ratio is. If that is less than 1, then it converges. So we're going to look at a formula for the sum of a infinite geometric series, so not the partial sum of the first n terms like we've been looking at, but the infinite geometric series. So we're going to add up infinitely many terms for a series that converges, and we're going to have a formula for how to find that sum. So we're going to start with our formula from last video. So the sum for a geometric series is a1 times 1 minus r to the n over 1 minus r. We know this series will only converge, it'll only have a sum if that common ratio has absolute value less than 1, so if it's a proper fraction. And if it's a proper fraction, then when we take that and raise it to very large powers, let n go to infinity, this will go to 0. As we take a fraction, raise it to larger and larger powers, it gets smaller and smaller. So that term, r to the n, as n goes to infinity, which is what we're looking at, infinite series, is going to approach 0. So what that leaves us with is a1, 1 minus 0 over 1 minus r. Right, and that's because we're letting n go to infinity. And so simplifying this is just a1 on top times 1 minus 0, which is just 1 over 1 minus r. And this is our formula for sum of an infinite geometric series. And remember, this will only work if it converges. Right, and the key for convergence is this right here. That common ratio has to be a proper fraction. So last thing we're going to do is do 2 examples where we actually use this formula. One where we just are finding the sum, and then the other one where we're actually doing an application, writing a repeated decimal as a fraction. So first we're going to find the sum of the convergent series from slide 4, where we had 1, 1/2, 1/4, 1/8, 1/16, 1/32, and just keep adding it up infinitely. So again, here we know our first term is 1, and our common ratio is 1/2. So all we have to do is just plug this into the formula. So the sum of this sequence, the series, the sum of the series, as n goes to infinity, the infinite series, we're just going to use that formula from the previous page. So we have a1 over 1 minus r. So in this case, the first term, a1, that's 1. 1 minus our common ratio is minus 1/2. And we're just going to simplify. That would be 1 over 1/2. And simplifying the fraction, that would be 2. So as we add this sequence up infinitely, it will be 2. It'll reach a finite sum of 2 if we keep adding these powers of 1/2 together. We can use the same idea to write a repeated decimal as a fraction in lowest terms. So the decimal 0.7, right, that's 0.7777, and it keeps going. That's the same as 7 over 10, writing out the decimal expansion, 7 over 100, 7 over 1,000, 7 over 10,000, and it'll just keep going infinitely. So we can apply the same formula that we used in the last problem. We know our first term is 7 over 10. And that our common ratio here, what are we multiplying by every time? Well, that's 1 over 10. So now we just use that exact same formula to find the sum. So we start with our first term, which is 7 over 10 over 1 minus the common ratio, 1 over 10. So that's 7 over 10 over 9 over 10. Right, dividing fractions, we flip and multiply, so that's 7 over 10 times 10 over 9. Our 10's cross cancel, and we have 7 over 9. So just like with the partial sum, so adding up the first n terms or generating the terms of the sequence, a lot of this comes back to using the formula, plugging in, being able to identify the first term and the common ratio. If you want to see some more examples for a different video, you can search for infinite geometric series.